This is problem 120 of Neetcode and 50 burst balloons. So we're going to be given an array of integers of size n. And basically every single position represents the, the value you get by bursting a balloon. And if you burst a balloon, the coins that you're going to get is basically the value of this balloon itself multiplied by its two neighbors. So for example, if you burst the balloon 2 here, well, the coins you will get is basically 4 times 2 times 3. So we'll get 24 coins. All right. And on the next round, well, if you burst 2, well, you're going to get an array with containing only 4, 3, and 7. And then you can decide to burst 4. And what happened if you burst a balloon that is on the edge? Well, you just assume that there's a 1 on the left and the right side of the array. So we're going to multiply 1 times 4 times 3. So we're going to have 12. And yeah, so that's what you're going to do. But the thing is that you're going to have to return the maximum amount of coins that you can receive. So you will see that this problem is actually not trivial, even for us humans. So if I give you these four numbers, 3, 1, 5, and 8, what will be the answer? Well, I can give you a couple seconds to think about it, but you'll see that it is not necessarily obvious, because one strategy will be like just burst the smallest value each time, but this is actually not going to work, because you will see that it is sometimes not going to lead to the optimal solution. So let's actually take a look at what will happen if we always burst the smallest value. So if I burst a 1, right, I will have to do 3 times 1 times 5. So this is the amount of coins I'm getting by bursting this balloon. So I'll just keep it in memory up there. So I have 15 up to now. And then I will start again. So I will have a 3, I will have a 5, and I will have a 8. All right. And now let's say I burst again a small balloon. So I'm going to burst this 3. So I'm going to have basically 1 times 3 times 5. So I'm going to have 15. All right. So now instead of this 15, I'll be at 30. And then I will start again. But this time I will only have a 5 and 8. So by bursting the smallest value, which is 5, I will have 1 times 5 times 8, which is 40. So I will be basically at 70. And lastly, I will simply have an 8 in my array. So I will have to burst it. And I will have 1 times 8 times 8. So I will end up my solution with 78. But I will show you how we can do better. So to start this out, we will still burst the balloon 1. So we're going to have 3 times 1 times 5. So we will be at 15. So I'll put 15 here. But now instead of bursting the 3, I will burst the 5. So by bursting the 5, I will do 3 times 5 times 8, which is 15 times 8, which is 120. So now our 15 is going to be 135. So you can see it right away. We just beat the previous score we did. So that's basically just a glimpse of how this thing works. And now I would like to bring your attention to a simple fact. The fact is that the last balloon that we are bursting is going to give us basically the amount of coins that its own value is, right? Because at the end, when you only have one value inside your array, you're just going to multiply it by the 2 ones that we assume just exist. Because this is what the problem tells us, that on the edges, you have like a 1 value that you use in your multiplication. So what we're going to do is that we are just going to multiply its value times 1. So this is what we're going to do for the last balloon we're bursting. So to solve this problem quite efficiently, we're going to use dynamic programming, and I will use a top-down approach because I will start from each balloon and I will say, what if I burst this balloon first, okay? So what if I burst this balloon first? I will basically have 3 plus um, the maximum you can do on this side and the maximum you can do on this side as well, right? So now if I start again, on my second call, I will have this array of 1, 5, and 8. And then for each values, I will say like, what if I burst this first? So my maximum value will be what is on the left, and my minimum value will be, my maximum value will be this 1 plus what is to the left and what is to the right, like this. Sorry for taking the exact same colors, that's super helpful. And again, on my third call, when I'm here, I will start basically this first value, and I will say, what if I start at this value? What is the maximum I can get? So it's going to be this 5 plus the maximum I can get to the right and the maximum I can get to the left. So notice that at some point, we're just going to get like a single value like 8, for example, and I will say, what if I burst this value? What is the maximum value I can get to the right? What is the maximum value I can get to the left? But actually at this point, there will be just 1 on each side. It's not gonna go any further. So this is like the bottom we're gonna reach. And by basically climbing this logic back to the surface, we're actually gonna know what is the maximum amount of coin we can retrieve. So that's the code we're gonna do. So we're gonna have a for loop. We're gonna go for every numbers, and we'll assume that this is the first number we are gonna burst, and we're gonna see what is the maximum we can have basically by adding this, by bursting this value in the last place, meaning that that this value is gonna basically appear in the equation as itself multiplied by 1, and then I will do this 1, and then I will do this 5. And I will pass this 8. So see that basically I will try every combinations, and I will set basically a max function that will set the maximum I can get for every single call. And on each call, when we are gonna like track back our way up to the surface, well, we're gonna basically provide this maximum value for every single call. And this is all by going back to the surface, just by calling this depth first search function on each entries inside our array. We're gonna get back our 78 with the first try. We're gonna say this is not optimal. We're gonna get back our 167, which is the value we had by finding the optimal solution, and we're just gonna pick that maximum value. So this is definitely not trivial, but let's go ahead and solve this. So the first thing that we want to do is that we want to update nums, because we know that nums has ones on the left and the right sides. And we also want to create a hash map, because we don't want to recalculate each values multiple times or end up in an infinite loop. So I will just have like my DP, which means basically scene value or scene pair of values. And then I will have my depth first search function, and in which I will just pass the left and right pointers. What I mean by left and right pointers is that when I said we are going to go through every single values, well, I'm still not explicitly, but I'm still saying that we are still in the range of the array. But when I try this value 3 and I want to see what is the maximum value I can get, or the maximum amount of coin I can get by bursting this value first, and then going to see the other sides of the left and the right one, well, then I actually want to modify this range to the right to be this, right? So this is why I'm setting a left and right pointers, because on the surface call, I actually want my range to be the entire array, but then on each sub call, I want to tighten a little bit my range until I find single values that I can return to the surface call. So this is why I'm passing inside my def search function a left and right pointers. And in my return statement, I will return the DFS, and the left pointers is basically going to be the index 1, because at the index 0, we're going to have the value 1, which is something we don't necessarily want to include inside our initial range. And the right pointer is going to be equal to the length of the nums minus 2. Minus 2, because if we only did minus 1, we will have reached the 1 here that we added at the end. So we're going to have to do minus 2. And now we are going to implement what is inside the def search function. So first of all, I want to check if the left pointer is greater than the right pointer, for which case I want to return 0. And the reason I don't just say greater or equal to is that the left and the right pointer will at some point be equal, and this is fine because we're just going to tell us that we're pointing at a single value, which is absolutely fine in our problem. But in a case where the left is actually getting greater than the right pointer, this is where we actually want to return a 0. Another statement is, what if the left and the right pointers now have already been seen? So in DP, so if this is in DP, we are going to return the values we already stored for them. So there's no need to recalculate that. So we're going to return this. And now we can actually start our call for all the values inside our initial range and or other range that we're going to have through our calls. So initially, I will just set a value inside our hash map for this particular position or for this particular range. This is initially going to be equal to 0. We'll eventually change that. And what I will do is that I will say for I in the range of, and I want to start at the left pointer and go up to the end of the range, right? So I'm going to have to say R plus 1. So I actually reach that R index. And what I want to do initially is that I want to set coins to be basically its value. So it's going to be, I'll create coins which will initially be equal to the nums at the index that is 1 out of bound of the left range, so the left boundary of this range, which will, for the first call, be equal to 1. And I want to multiply this by the nums at the index I, so that particular value we're seeing right now. And I want to multiply this also by right R plus 1, because I want to take the index that is out of bound to the right. So this is how we are basically saying within that range, basically, what if that particular value at the index I is burst the last? If it is burst the last, it means that we are going to multiply this value plus the 2 values that are out of range. And the 2 values that are currently out of range to the left and to the right in the initial call are going to be basically our 2 ones here, because our current range is just going to take the first index, or the index at the position of the index 1, and go up to the last value of our array. It's not going to contain the 2 ones we added. Okay, and now what we want to do with our coins is basically to add the maximum value we can get from the left side of this value and the right side of this value within our range. So what we're going to do is that I will call it DFS, and I will say that I want to basically bound this at the left index right now. And I want to take the left side of this index. So I will just say I minus 1. And the right side of our current index is going to be basically I plus 1, but it's going to be bounded by the right index, right? And now I want to set the DP at this particular position. So at this, at this particular range, this is going to be equal to the maximum between its current value and the coins we just calculated, so that at the end of our call, for each call and for each range and sub-ranges, we get this DP maximum value that we're going to return here. Right, and this is going to tell us on the surface level what is the maximum amount of coins we can retrieve. So let's test this code out. And this works. Awesome. So the space complexity of this problem um, is basically going to be n squared, because for each value we're going to have a subrange, and for inside each values of this subrange we're also going to have another value. So this is going to be an n squared that is going to be stored inside our DP memory. And for the time complexity, basically we're going to have a big O of n3. This is a little bit more complex to explain, but what we're doing basically is that we are going to take all the possible ranges, and for each of these ranges we're going to go see every single values, and for each of these values we are going to go see every single ranges, um, meaning that this is going to give us a time complexity of big O of n3. So with that being said, I hope you enjoyed the video, and I hope to see you in the next one.